Welcome back, chemistry fans. Today, what we are going to do is finish up Unit 13. This is all about buffers. So let's go and find out what the final piece of the puzzle is for acids and bases. It shouldn't be too much more. We've already talked about one of the key formulas. There's just a little bit of a nuance that we've got to adapt to it. So let's jump into it right now. A buffering solution is a material that you can add, and what it does is it eats the acid that you may add to it. And it sounds very odd because this buffering solution is actually made up of a weak acid or a conjugate acid. It's made up of acid and base particles, but for some reason it is able to actually consume any additional strong acid that you add to it. Or just opposite, it could eat and it could get rid of the strong base that is added to it. So it involves knowing that amphoteric, amphiprotic terms. So these are materials, these weak acids, that they're okay if you give them hydrogens or if they give off hydrogens. So in that process, as you add more hydrogens, more strong acid to the solution, it continues to consume it and not allow it to be free, so the pH never goes down. So it's a very good system. And it's what is dynamic about what's going on in our stomach to try and always balance out any materials that we consume that might upset our pH in our body. So again, how this occurs is it must be a weak acid and a weak base. They must both be the starting point for the solution. If we have those, it doesn't matter if you add more H because the weak base will bond to it. It doesn't matter if you add more OH because the weak acid will bond to it, and they will neutralize whatever you add. So here's how it works. So what you will notice in this picture is that if you do not have a buffer, and those are over here on the left, if you just have some regular water, and you add some acid, a strong acid, notice what happens to the pH. It starts at 7 with water and it goes down to 3. But if you have a buffering system in this water, if you add a buffer, which is a weak acid, weak base, if it starts at the same pH of 7, you add that strong acid to it and it doesn't change its pH. The same thing is happening over here with the base. If we have water, we don't have a buffer, the pH goes up. But if you have a buffering solution, the pH is not going to go up that much. So here's what it's going to look like whenever we graph this. So before, whenever we had a pH titration curve, we had this same straight up. But what we didn't have is this longer amount of time, as well as an increased amount of base that you were having to add, because it continues to consume it. Well, at some point you overwhelm the weak acid and it no longer is able to eat it to maintain the pH. Now the pH slightly goes up, but at some point you overwhelm it and then it starts to look like our normal curve. So what you're wanting to look for is this long period where the solution starts to try and slowly increase. We call that place the buffering region of the graph. Now the equivalence point is in a same location. It's the halfway point of the graph, but here's another unique point where the pH and the pKa are equal right at the quarter or half of the buffering region. So the half point distance between where you establish the equivalent point and the starting point, that's going to be where the pH is equal to the pKa. That would be important for us to know, or we could say the same if we were doing this graph with bases, so that we can make some calculations later based off of graph data. So if, again, here's what we would need to understand right here at this point, this half point, where it is now going to be in equal portions of acid and base, not where the pH is equal, but where acid and base are going to be equal is up here, but where I have half as much. And that is going to be where the pH is equal to the pKa. And that same point is over here, but we started high because we started with a base. So this would be where the pKb is equal to the pOH in this case. All right, moving on. How do we deal with it as a mathematical? We have already seen this equation, the Henderson-Hasselbalch equation. So we would be needing to, the hardest part for you will identify what is the base and what is the acid. So we're looking for that change where the H is no longer present, that base goes on top. And then we would have to be given some of these other pieces of data for us to calculate it. Okay, so let's take what we've got and let's see if we can solve. So here was our equation. It is pH is equal to the pKa plus the log, the log of the base over the acid. Okay, so now again, the math is probably not too difficult for you, but the hardest part for us is going to be identify which is the base and which is the acid. Both of these are weak conjugate pair. Neither one of those is a strong acid, strong base. So what we have to see is which one of these has the H in it. Well, that's clear here. So that's my acid. So that concentration is what's going to go on the bottom. So I've got log of 0.25, and by default, this is going to be my base. This Na is going to leave, and it's going to have just the acid particle, the C2H3O2 left over. The pKa, well, we're given a Ka, so what we have to do is we have to do just like we did for pH. Remember, the formula for pH is equal to negative log of the hydrogen ion concentration. Well, the pKa is going to be equal to negative log of the Ka value. So that's what we're going to do. So we're going to do the negative log of 1.8 to the -5 exponent. And what we get there for that is a 4.74. So now let's simplify this ratio of 0.15 divided by 0.25, and you get 0.6. So the log of 0.6. Now notice what happens here. It becomes a negative. So I've got 4.74 minus 0.22. That's going to be equal to our pH. So 4.74 minus 0.22, and I get 4.52 as my new pH. So it just slightly changes it from where it would be. Okay, this is another problem of the exact same caliber, so I think we're okay with just this one practice problem. Thank you very much for paying attention. I will talk with you again soon. Farewell. Goodbye.